from last night, because what you'll notice is that that's a version of balancing that we use probably 10% of the time, whereas the acid and base balancing that we're going to do today is more 90% of the time. So I'm going to prioritize and use more time for that today so that you can get some practice in, so that you don't have to do much at home tonight, because you have a half test tomorrow. Okay, so we did not do this one in class. Out of 1, 3, 6, and 7, which one do I need to do?
6.
I hear 6, and maybe 3, and maybe 10. Okay, let me start with 6. In terms of writing these out, it's easy. I mean, you're going to have to write these reactions on your paper, right? So your phones are away, you have your paper out, you're checking your homework or writing your homework along with me if you were unable to achieve this. So we have sodium iodate, HCl, yield sodium chloride, iodine, and H2O. As you wrote your oxidation states above the numbers, above the symbols, which were the ones that were changing, that were involved in redox? Iodine, so this was I'm going to have to write this out kind of small, but -2 for the oxygen, a +1 for the sodium. What was ion's oxidation state? +5, okay? And then this one was -1, this was a +1. Hydrochloric, so I'm just going to go really quickly put these on here. -1, +1. Iodine, 0. Water, -2, and +1. Okay, so we saw the iodine from the iodate going from +5 to 0, and then iodide going from -1 to 0. So they ended up going to the same product, and that's okay. A lot of times we'll have the same reactant being both oxidized and reduced, meaning it goes to two different components of the product. This is just the opposite. We have two different reactants going to the same product. So it's similar. It's called a disproportionate redox reaction. Okay, so the +5 to 0, what's happening to that one? Gaining or losing electrons? Gaining 5 electrons. So rig, because it's being reduced, and now I'm just going to put 5 electrons in there for my own sake. And then the -1 going to 0 does what? Loses 1 electron. So oil, 1 electron. So the electrons lost must be the same number of electrons gained. What would be a multiplier that would do that for us? So 5, so we're going to multiply the number 1 electron by 5, and this one we're going to keep it as 1. So when I multiply this by 5, what you'll notice is that this needs to be applied to both so iodine, and the sodium iodide. So for sure I'm going to go ahead and put the 5 there, right? But wait, if I put a 5 here, and I put a 5 here, are my iodines in the entire structure balanced? No. Okay, so I know I'm balancing charge right now, but Courtney, I think I talked to you on this one yesterday. Tell me our logic here.
I think we put another 5 in front of sodium iodate at the beginning.
Okay, so if we put a 5 there,
Yeah.
so true, but the electron count won't be.
I think we talked about the sodium stuff.
We talked about the sodiums, not the iodines.
Yeah.
That's what we talked about. Okay,
Yeah.
because I was like, I remember helping someone along this. So if we put the 5 here and here, we know that the electrons seem to be balanced, right? But look here, 5 transferred here, 5 electrons transferred here. But then our iodines, we have 5 iodines here, but 10 over here. So we have to come up with a happy medium. And my happy medium was not to put a 5 here. So I'll tell you why. So if I have 5 iodines here, and I have 1 here, how many iodines do I have total? 6. And so whenever I take this, remember this was a temporary coefficient. Whenever I take that, I hope I'm videoing right now. Whenever I take that into consideration, yes, okay, just making sure. When I take that into consideration, I can always adjust if needed. So if I have 6 iodines on this side, and what coefficient would I need here? Truly a 3. So I'm going to try to adjust that. There's a 3. Okay, so this transfer, I'm not changing, I am changing the coefficient, but I'm going to walk you through the electron count in just a second. Because there's no other coefficients for me to add, because this down here was a 1, I need to now look at non-redox atoms. So non-redox atoms, how many sodiums do I have on the reactant side? 6, okay, so how many do I need, or what do I need to add on this side? So put a 6 in front of the sodium chloride, okay. How many fluorines do I have on the product side? 6, so what do I need on the reactant side? 6 in front of the HCl. Okay, how many H pluses do I have, or H's? 6 on this side, what do I need on this side? So I need to put a 3 coefficient, and then I'm saving oxygens because they were embedded. So 3 oxygens on this side, right? 3 oxygens on this side, we're good, right? So all the mass has been balanced. And so to walk you back through this, from 5 to 0, if I have 1 going there, but we have 6 total iodines over here, that means 5 times 6 is 30, and then 30 electrons. I want to explain this correctly, but this one's a little bit weird with the disproportionate. I should probably not give you this one. So the iodine here from 1 to 0, but we have how many of them? 5. No, that's not how. Let me come back to this one. I need to explain this one better for you guys, because as I was balancing the mass, it prioritized this number be 3 versus the charge. Can I come back to this for a second? Because they have explained it better on my sheet for myself. Okay, let me come back to that one. 10 or 3 first? 3. So this is the ion state charge, or ion charge balancing. It's just not as used as frequently, but we do need to know how to do it. So this one we did a similar one, but not quite this one. Which were the 2 elements involved in redox? So this was a +7, and this was a +2, and then which one? Other one? Carbon. This one was a +3, and we did that last, right? So we had the oxygen that was a -2, so -2 times 4 is -8, and then this H plus was a H was a +1, so -8 and a +2 together makes a +6. So how do you balance that out? You need a -6, you need a +6 to balance that out. So +6 divided by 2 is a +3. So I'm not jumping straight to that. That was like the last thing decided. Question?
Yeah, why is the second magnesium,
Manganese?
Yeah, is it +2? Because I thought it was +1.
Because I can tell you 2 different ways, okay? So in terms of looking at this as an ionic compound, the MnSO4 is 2 different ions, right? So SO4 has a -2 charge, or oxidation's no charge. So the manganese needs a charge to offset that, so that definitely would be a +2 in terms of the compound. Or assigned an oxidation states of -2, that's a -8. And then this has got to be the ionic charge, which in this case is a +2. And then your sulfur would be a +6. So you can go through all your states as well, but it's actually an ion in this compound. Okay, so this is a +2. My pen is really off. And then what about this carbon? +4. Okay. So as we go from manganese to manganese, what's happening? Gaining how many? 5 electrons. And then carbon to carbon, oxidation is lost, okay, and so there's each carbon is losing 1, right? But I can already see that this carbon and this carbon, they're not balanced in their number, much less its charge at this point in time. We don't see carbon anywhere else, right? Okay, so let me just think about this for a second. If I need to adjust to put a 2 coefficient here temporarily to make sure that I have carbons balanced, as I do that, that means total I have how many electrons transferred? 2 carbons, each of them losing 1, losing 1, so it's going to be 2 electrons total. Compare that to this one of 5. What would be your temporary coefficients for the time being to balance the charge? This potassium permanganate and manganese 2 sulfate would get what? Anybody? Give me your best shot here. So we put a 2 there, right? If we put a 2 here and here, how many electrons total are transferred here? 10. So 5 electrons was transferred in the manganese to manganese, and now I've doubled that, right? So I put the multiplier of 2 here to give us 10 total electrons transferred. Well, then again, I need to have 10 total electrons transferred on the top one. So I've already have 2 transferred from this. What would be a good multiplier to get 2 to 10 would be 5, right? So I need to put a 5 in front of this one, right? But when I put a 5, I can't just replace this with a 5. I need to consider that I had 2 there, and now I'm multiplying that by 5, so what would be my new coefficient here? 10. So that temporary part there is part of partially balancing the charge, but also partially balancing the mass. But what you'll notice is I'm still balanced in mass. 5 times 2 is 10 carbons, and I have 10 carbons here. All right, so I have 10 electrons transferred top and bottom. Don't mess with these coefficients that I have in red right now anymore. Let's go ahead and finish balancing. So how many potassiums do I have? 2 and 2, we're good. Manganese, 2, 2, good. Saving oxygens because there's a ton of them. I'm waiting on that one. Let's go to sulfur. How many sulfurs do I have? 1 here, but on the side. No. 3. 2 and 1 is 3, right? So what do I need over here? A 3 here. And since I've basically got hydrogens balanced on this side, right? How many hydrogens total in the reactants? So 5 times 2 is 10, plus 6 is 16, right? 16, so for the only hydrogen that's over here, what do I need? 8. It's only on this side of the board. Okay, so I got 16 hydrogens. Oxygens now. So how many oxygens total on this side? 40? 40 oxygens on that side. How many on this side? 24, 32, 40. Yeah, 40. Okay. So that was that adjustment that we did at the beginning was very important, but otherwise it helped us balance our mass and our charge at the same time. Okay. This oxidation state balancing is important, but it's not the utmost important one. So what I want to do is I can transition to acid-base balancing. Okay. So we have a lab, and I haven't printed it out for you yet. It's next week, and it basically has us do a titration with potassium permanganate. Does anybody know what color potassium permanganate is? So potassium permanganate has manganese is what color? I mean, manganese is what oxidation state? Manganese is a +7 right here, oxidation state, right? Manganese is the only transition metal in this thing. It controls the color. And I showed you guys yesterday. Let me show you. I showed you this picture right here. Okay, so look at manganese and what color is it? It's hard to see. It's like a grape purple color. It's the prettiest compound I have. It's my favorite one. So basically, we're going to be doing a titration with that, but we have to acidify this titration. So acidifies means to add excess acid. And so when we are doing this balancing act here, we have to consider the excess acid in our solution as a whole, which means we have to balance a reaction in acid. So balancing in acid is our next topic. And it's related to the fact that sometimes acids are needed for acid catalysis. So write down this little introductory part, just the concept. I can write all this down. I'll help you understand what it means in a second. So now we're going to consider balancing in the presence of excess acid. So a lot of times reactions will not occur very, very quickly unless you give it a catalyst. What does the catalyst do? It speeds up a chemical reaction, okay? So we know that it speeds up a reaction, but the how part is going to be later on in our chem lives together. But it helps something stop reversing itself too. So we're going to run into a lot of reactions that are reversible, where it forms products and then immediately reverses and reforms reactants and so forth. It's called a reversible reaction. It's going to be when we hit equilibrium later on. And so our reversible reactions are the ones that have reversible errors like that. So if we add an acid as a catalyst, it may or may not catalyze both forward and reverse reactions, so we try to use them very specifically. So one example is an organic reaction with ethanoic acid and ethanol. There's a lot that deal with organic reactions. But hey, Alvin, today we're going to not really go with as many organics. Today we're going to go with simple ones. So an ester, you guys remember Esther? She's a nice lady.
we haven't talked about her very often, but ether is someone comes in something on either side, right? And ester is another form of another functional group that we don't talk about all that often. So the way you'll see these acid catalyses
Denoted is like this.
it'll be on an arrow, and it'll say H plus is a catalyst. And reflux just means that you do it until completion. Don't worry about that part, but you'll see it written like this. Well, also the acid is used in the balancing act, so we have to include it as a reactant or a product or both, based on the needs of the atomic numbers, the masses, and the charges. So we're really gonna apply this, but this is like why it's important, because acids are used to help with reactions. They serve as a catalyst. Don't worry about the specific reactions at all, guys. But a lot of times the acid that we choose to utilize is sulfuric acid. So that's why you'll see,
Sulfuric acid.
but you'll see sulfuric acid used as a catalyst quite a bit. So if you ever see a reaction that says potassium permanganate and potassium permanganate and sodium dichromate are reacted in the presence of an acid, this is what we're doing. So in the presence of an acid is where this comes into play. Do not write all of this down. You're only writing down that part right there. Okay. So I'm going to actually let you write down the rules today first. I will go back. The reactions really are not that hard. It's the opportunity that acids have to react. That's all. I'll let you write down the rules first, and then we'll write and apply them. We just remember two questions. So in terms of approaching a problem, like a balancing with an acid, generally I'll give you the full-out reactants yield products. Your job is to first figure out what thing is going to be oxidized and what thing is reduced. You do that by just taking the equation and breaking it into two halves, which we call our half reactions. I'm going to do a couple models through this. And so that's what this right here is, divide equation into half reactions. Whenever you balance into the half reactions, you'll find that some of these atoms are not balanced in number. Okay, so you're going to start balancing things that are not H's and O's. After you've considered that, then you would start to add water. Water is always present in all reactions that we generally deal with aqueous solutions. So water helps us balance out one of the components. After we've added the water to balance the oxygens, then we start adding in H pluses, because we have this whole reactions happening in the presence of an acid. So we've got plenty of H pluses to help with our balancing of atoms. After we've balanced atoms in this case, then you're going to consider charge. So in the first type, we consider charge first and then atoms. This one we're doing atoms first and then charge. And so after we've added or considered the charges, that's when we're going to add either electrons on the products or the reactants based on where the charge is needed. We've just split this reaction apart into two, where they need to put it back together so it's a full reaction. Right now this is gibberish to you, I feel. Let's do an example to help it make more sense. Yeah. Not yet. I'll go back later. And I'm video, so you can look at it by yourself. So let me come back. This was my more detailed words. The first one was a little bit more simple. So let me show you an example. And you can write down this example or you can watch, but I want to give you at least a model of one before I start writing them out. So I've got an example here with potassium dichromate and iron 2 sulfate. and I give you the two products plus the K plus is a spectator. And so as you're looking, you can see some consistencies from reactants to products. The consistencies are the chromates and the chromium over here are actually still present because you can't cancel out through spectator as a spectator ion the chromium because it's in an ion, it's in a polyatomic ion right here. And then second, you can see the iron, which is a 2 plus here, going to an iron is a 3 plus over here. So if the ion charge is changed, that means the oxidation states of that particular atom has also changed. The sulfates, you know, sulfate and sulfate, these things right here are soluble. The sulfates will cancel out as spectator ions. The potassiums will cancel out as spectator ions. So really, the only thing present is what I have. The only thing reacting, everything's present still. The only thing actually reacting is what I have right here. Dichromate and the iron 2 yield chromium 3 and iron 3. But what you've noticed is that it looks like the oxygen has disappeared. That's because it's not balanced yet. So all I did was I took my big boy reaction and I minimized it down to something that was more reasonable in terms of something that's actually reacting, kind of like the NIE. You with me so far? Okay, so then what two things go together from reactants to products? What two things are going hand in hand with each other? Dichromate goes with chromium. That's our first half reaction. And then iron 2 and iron 3 go together as our second half reaction. So we take our reaction, we break it into two things that relate to each other. So write out your two half reactions underneath each other just like this. And if you're starting with me now, thinking it now, this is one that you might want to write down or pay really close attention to. So the dichromate going to chromium 3, as you look back at your notes that you just wrote down the steps on, the very, very first thing to do is to balance the non-O's and H's, right? So chromium is a non-OH, so I put a 2 here to balance the 2 for chromium. I'm going to get to iron 1 in just a second. So I'm going to go ahead and stick with this one. So what's my next step? What's it say to do after you balance your non-O's and H? Add water to balance out the oxygens, right? So I have on the reactant side 7 oxygens. I need to add 7 waters to the product side to balance out those 7 oxygens. Now my oxygens are balanced. Now I need to balance my H's. How many H's are on the product side? 14. 7 times 2 is 14, right? So now I add, to balance H's, I add H plus because I have a surplus of acid. I add 14 H pluses on the reactant side. Okay, so all atoms are balanced, yes? H's, chromiums, and oxygens. You got me? Okay, I'll get to the second half reaction in a minute. Now what I have to do is I have to balance the charge. So my charges are literally the ion charges. So on this total side over here, what's my net charge? 6 plus, right? 2 times 3 plus is 6 plus. And I'm going to just write that above here. And I think it's helpful to, I usually just put a bracket. I'm like, this whole thing over here is a max as a net charge of 6 plus. What about this whole thing over here? Say again? 12 plus. Do you see that? 14 pluses is 14 plus, but then a 2 negative drops me down to 12 plus. Okay, so this over here is a 12 plus charge. So now I need to add electrons, because it's all about the electrons being transferred, right? They're being transferred between first half reaction, second half reaction. Where would I add electrons to make the charges equal? To the reactant side, right? I have 12 plus, I have 6 plus. How many electrons do I need on this side? 6, and I'm squeezing this in here. You guys have more space. You're adding 6 electrons in here. Is that half reaction oxidized or reduced? Say again? Somebody just said it. It's reduced. Do you remember yesterday I said if the reactants have the electrons, they are being reduced. Okay? And notice I didn't even write an oxidation state at all, guys. So sometimes you might need to consider writing oxidation states, and just to verify with yourself, you're like, make sure it's reduced. What's chromium's oxidation state here? Do that in your head real fast. Plus 7? 6, right? So oxygen is this is a 2 minus and 7, so there's negative 14 there. Negative 14 plus something is equal to negative 2, so negative 12. That's going to be a plus 6. So this is a plus 6 oxidation state. This is a plus 3. Was it reduced? Yeah, 6 plus down to 3 plus brings us down, so we gained electrons, so it's correct that we were reduced. So that's just a double check that you were reduced. Okay, next one is this one. So starting back from the top of our rules, is it balanced by non-O's and H's? Yeah. Does it need to know an H? No. Okay, do I need a balanced charge? Yes. Okay, charge on the sides, 3 plus. Charge on the sides of 2 plus. Who gets the electrons? Products, how many? Okay, so 1 electron. Okay, this is actually now oxidized or reduced? Oxidized. Okay, so we're good so far. You always have to have 1 oxidized, 1 reduced. Are the electrons that are happening between these two half reactions balanced? No. So now what you have to do is you have to add a coefficient or a multiplier to make the electrons balance. I have 6 electrons in the top reaction. I have 1 down here. What do I need to do? So multiply the bottom reaction entirely by 6. Okay, and I'm actually show you my work from here on because I have it's a mess right now for me. So we've done this step where we added our waters. We've added our charge here for the 1, and then we're timesing the bottom reaction by 6 to balance the electrons lost and gained. So in my step 4 right here that I have demonstrated, already typed out, my computer, guys, it's having a hard time today. Oh my gosh. Okay. So step 4, this reaction plus this reaction with the 6 multiplier makes me total down to 6 electrons, 14 H pluses, a dichromate, 6 Fe2 pluses, and then also bring down, this is us basically taking our 2 reactions back into 1, taking our chromium 2 plus, 7 waters, and then 6 Fe3 pluses into 6 electrons. So this is us like netting all the half reactions. Then we have to go ahead and cancel out things I can cancel on left and right. So you'll notice that the same exact things appear, 6 electrons, and that should every single time cancel. You should never have leftover electrons. That would mean that you never balanced your charges. Rebalanced charges, they don't exist as a net. Anything else doesn't simplify? No. Sometimes you'll have H pluses on both sides, and sometimes you'll have waters on both sides, so you have to simplify. But right now, that's not the case. Now, I know that looks really crazy, a lot of work, right? But you get the hang of it very quickly, and you start to move through it. It's just a rote process. So let's go ahead and do maybe 2 together instead of on the board like I have here. Can I go forward? And I'm going to see if I can pick from your actual homework so I can maybe do a couple of those with you. So on your redox by half reactions, acid solutions, let's kind of go through 1, 2, and 3 together. Let's see where we are. These are all half reactions at the very top of your paper with the bismuth and such. Those are all just half reactions. I think I walked through that well enough with you guys. I'm going to start with this one. So what's the name of that? S2O3 2 minus. Thiosulfate. All right. So thiosulfate. Next. And what? What's OCl minus? You're like, gosh, nomenclature. What is it? Hypochlorite. Thank you. Okay. So, and this one over here is peroxydisulfate. Anyway, so do you guys see this on your paper? Yes? If not, let's just go for it. We got to do these together. So here's my reaction. I have actually already given you the net, the NIE, basically. Let's take it into 2 half reactions. Somebody tell me the first half reaction. What 2 things go together? S2O3 2 minus yields S4O6 2 minus. That's your first half reaction. Second half reaction? OCl minus and Cl minus. Okay, so you've written down your 2 half reactions. Next step. Balance non-HO atoms, right? Okay.
Sulfur we have 2, sulfur we have 4. Oxygen we have 3, oxygen we have 6. Let's look at the sulfurs right now. What can I do to balance this? So just add a coefficient of 2, right? Okay, does that handle the whole shebang? Yeah, it does. So 2 sulfurs are balanced. I mean, sorry, 4 sulfurs and 6 oxygens are balanced. So do I need to add waters? No. What's my next step? Do I need to add H pluses? No. So now let's look at charges. What's the net charge on this side? You're right. So the net over here is 4 minus, because 2 times negative 2 is 4, negative 4. And then this side, 2 minus. Where do I add electrons to make them equal? To the products. How many do I add? 2. Adding 2 electrons. Okay. First one's done. Mass and charge. Next one. Chlorines are balanced, yes? What's my next step? How many? 1 to the product side. Okay. What's next? How many? 2 H pluses, because I need to balance out my H's. Okay. Now I'm good with atoms. Let's go to charge. Net charge on the side. +1, right? So if you can tell me negative or plus, that'd be great. So this is a 2 plus and a 1 minus makes a 1 plus overall. And then this side, do you see it? 1 minus. This is a negative 1, right? 1 minus on this side, 1 plus on this side. Where do I add my electrons? How many? 2. Negative. We need to get that +1 down to -1 by adding 2 electrons to it. And is 1 oxidized and 1 reduced? Yes. Do we have balanced electrons? Yes. So I don't need to multiply anything, right? What do I need to do now? So sum and simplify. Okay, so I'm going to put a line here, sum these. What can you already tell is going to cancel out? And they should, right? If they don't, you got a problem. These electrons, 2 and 2, should cancel themselves out. And otherwise, everything else stays. 2 H pluses plus 2 thiosulfates, include your ions and everything. Hypochlorite yields peroxydisulfate, chlorine, and water. And that, guys, is balancing an acid. Okay? I'm going to give you guys a chance to work a little bit within your groups. So I want you guys to do, oh, I have this on my sheet, on my homework. After about 20 minutes, I'm going to show you how to balance in base. So I want you to knock out balancing an acid. So right now, do 1, go down to 5. So under the B, balance and I, so those 1, 5. I'm going to write these on the board. I chose about half of them. 1, 2, 5, 6, 8, 11, 14, 16, 17. Do those right now. And just for fun, I'm going to work out some of these on the board. So do you need help? I'm going to be working through a couple. Oh, I know this is for attendance now. Say again?
I thought it was supposed to be the one prize that you see. I'm so confused.
I just did 2. Yeah, I'm doing. Oh, I'm doing 4. I need to do 5.
I'll just leave that there for now. Did I do 2? My numbers are messed up on my board.
Yeah, I just did 2.
My numbers are really messed up on my board.
We got 2 pluses. So
Can I just do a quick check to see if we're okay on number 2 and number 5? So number 2, look back up here real quick. You with me? You got 4H plus 2 nitrates plus 1 copper yields 2 nitrogen dioxides plus copper 2 plus 2 waters. This is number 2. Okay. So you had the balancing act of 2 electrons for the copper and 1 electron for the first half reaction, and so you multiply the entire first half reaction by 2, and then you sum them. I canceled my electrons as I was going. So I will review that if I need to. I'm going to leave it there. I'm going to go over 5 in about a minute.
So now I need to go.
Oh wait. It's 9. Oh, that's 9. That's 9. So that's 1. Oh wait. Yeah, wait. So there's 9 and then there's 1. Yeah. You 10. Just 10.
Oh, okay. Savannah will be coughing in here. I'm getting over my cold. Now my husband's
I don't
got
usually
it.
come sick. I just
So you think.
Hope not. Okay, I'll put five up here shortly. Focus, my children. Thank you. I knew you were watching, waiting. What number are you guys on?
Thank you. Oh. And she multiplied by 5.
So simplifying for us. So in this case, if I have 18 H pluses and 14 H pluses, that is truly only 4 H pluses.
I got
Right, if you're in the middle, just finish your thought. I need to review 5 and 6 with you real quickly. So just finish your thought and then eyes up here. All right, eyes up here for 5, unless you feel like you're a beast, but just work with me here. Whenever you saw this one, you wrote your half reactions. The very first one I saw was zinc, and that's really easy to accomplish. Zinc to zinc 2 plus 2 electrons are then added, and that's done. That one is oxidized or reduced. Is it losing or gaining electrons? Oxidized. Okay, so the next one, you absolutely got to make sure your electrons are on the reactant side. So you have your nitrate and nitrate. You saw that the ends were balanced for good. You then balanced your oxygens by putting 3 waters on the product side. Those 3 waters also carry with them 6 hydrogens plus the 4 hydrogens that were here. So then you were like, I have 10 hydrogens on the reactant side. Great. Net charge, though, you consider everything. So there's 10 H pluses, so it's 10 plus. 1 minus means there's a 9 plus charge over here as a whole. And I write this for myself because I talk to myself the entire time on these problems because they have a step-by-step process you need to confirm. On the product side, you only have 1 H plus, or sorry, you have a plus sign, nothing else, so it's 1 plus. So the balancing act between that would be 9 plus needs to get down to 1 plus, so I need to add 8 electrons on the reactant side. And that makes sense, I should be adding them to the reactant side, so that's your double check. But then I need to get 8 electrons equal to 2 electrons, but that can't work until I put a multiplier involved in the zinc reaction. So 4 times all the zinc stuff, and then the 8 stays with me. And of course my 4 times 2 is 8 electrons, so they will cancel. And what I'm doing is I'm simplifying that in my head and I'm not writing it in the final reaction. So give me a thumbs up if you got 4 zincs plus 10 H pluses, 1 nitrate yields 4 zinc, 2 pluses, ammonium, and 3 waters. Yeah. Alright, do I leave this here anymore? I'm gonna leave it there for a second. 6 is next, and I had a couple of people asking good questions about the simplification process. In chemistry, if you have the same thing on both sides, the numbers of them can be subtracted from one another. So on 6, and you may not have gotten that far, but I'm going to walk through the bottom part. So 6, if you wish to look up here, it's up here. Whenever I got down to the bottom, and I'll let you do your top part, but when I got down to the bottom, I just put everything down, including waters and H pluses on both sides. So I had 7 waters on the reactants and 9 waters on the products. That is that's redundant to put water on there twice. So I need to simplify the side that I can. That's me taking away all 7 waters from the reactants and equally taking away 7 waters from the products. So I dropped my 7 waters down, my 9 waters, subtracted 7, I dropped it down to 2 waters. If you were watching, do you understand what I did there? Okay. And then my 18 H pluses and my 14 H pluses, on both sides, that's redundant again. So we need to simplify by taking away all 14 H pluses, all 14 that I can, leaving me with 4 H pluses on the reactant side. So once you guys work a couple of minutes longer on there, and then we'll do the bases when Vicky gets back. Yeah. 8, ready.
Okay, so, the one side,
Yes, do 2 and 5. Thought I was on silent. Who is calling me? It's a 90. It's like a. It's 980.
Oh, yeah, sorry. Oh, where's Binky? He's gonna come back. I gotta do bases. Don't be confused, Jack.
No, I wrote down. I wrote down. I wrote down part number 8.
Oh, yeah. That'll hurt you every time.
Yeah, I will.
Goodness gracious. Who are those? Thank you. All right. Yeah, no. Good. All right, in 1 minute I'm doing bases with you, so finish the one you're on. One second. Let me simplify my life here. 30 H pluses and 16 H pluses. 14 H pluses. Who's done 8? This is 8? Who's done 8? Alright, let's double check this together. If you've done 8, in the end, you should have 2 manganese, 2 pluses. 14 H pluses. 5 BiO3 1 minuses yields 2 permanganates. 5 Bi 3 pluses and 7 waters. Score. All right. All right, finish the one you're on, then we're doing bases. It's not that I don't want you to finish, but I need to do at least one example with you. Yes. Not number 6, number 8. Yeah.
All right, eyes and ears. I need them. I got 17 minutes. We're gonna do at least one. Ready? Ears out. Take it easy. Okay. So when we do bases, so that whole idea was we have an acid, we're balancing an acid, we have to include this excess H plus present. But now if we have instead, we're catalyzing a reaction with a base, because bases can just as well catalyze a reaction. We're going to balance it almost exactly the same way, except for when we get to the H plus component. H plus is because there's an acid, right? What would bases include? OH minuses. So we're going to balance just like we would acid. When we get to the part where we've already added our H pluses, because we've mastered the acid balancing, right? We feel pretty good about that. If we've mastered that, then let's not change, like reinvent the wheel. Let's just tack on a rule. So we're going to add the H pluses just like we've always done. But before we start combining and balancing, before we do that, we're going to add just the same amount of OHs as we have H pluses. However, I usually only have H plus on one side of the half reaction, right? But if I add an OH to the H pluses, I'm also changing the charge because I'm adding negatives now, right? I've already mastered like my electrons, right? I already have my electrons done. Don't screw up your charge. So if you add in like eight hydroxides on one side, add the same number of hydroxides on the other side. That way your charge balance remains. So I'm gonna walk you through an example with that. But if you also notice OH and H plus together, they're not gonna stay separate, they're gonna combine together to make water. Okay, so there should be no excess H pluses present because you're not balancing an acid, you're balancing a base. The only thing that would be present in the end as an ion would only be some OH minuses that never got neutralized from the H pluses to form water. Cancel anything the same, specifically waters, because that's really what the problem's going to be as your simplification process occurs. So let's go through a whole one. Yeah.
So would you still add the waters though too?
Yeah, because your waters were already taken care of before your H pluses were. Remember, you're adding water before H plus. All right, I think an example would be best to do now. I have my example from previous, so, but I'm going to do a fresh start here. So, on your sheet, let me pull up your sheet. I'm going to find it. Let's do the first one, chromium and sulfate or sulfide, etc. Let's balance it just as if we had an acid. Let's go ahead and do that quickly. Use your half reactions. Was everybody able to get the sulfide and sulfur with 2 electrons to balance? And then your chromiums were balanced. You needed to balance your oxygens by adding 2 more waters on the product side. Those 2 waters brought with them 2 H pluses, so you balance the H pluses by adding 4. Yeah. So generally it will say this reaction is in the presence of acid or in the presence of base. It'll say it in the problem, but this whole problem sets for bases right now, so that's what I'm assuming you're understanding with balancing bases. But I haven't even done the base step yet, so hold on. So we added our 4 H pluses to balance our H's, and then we saw net charge of 4 plus and 2 minus is a 2 plus on this side, right? And then a 1 minus on this side. So how do I get 2 plus down to 1 minus? I add 3 electrons. Still though, I've got to go ahead and make sure my electrons are balanced, just like our acids ones. What do I need to do now? Okay, so top by 2, bottom by 3. So times 2. I'm going to try to do it as the summation step so that this will very much resemble our acid one. Alright, so let's go ahead and sum this and let's see what we can plug in our OHs. So you have, I know that electrons cancel, I'm not going to write them. That's 8 H pluses, right? 2 chromates, 3 sulfides, yielding 2 CrO2 1 minuses, 4 waters, plus 3 sulfate, or sulfurs. Okay, so we know how to get this far. We can use the acid. Where do you see an excess of H pluses? And the reactants right now. So I'm going to go ahead and take out those H pluses. They cannot exist in base. So everything is balanced, atoms and charge. Do not screw that up. Whatever you add to both sides, and that's it. These 8 H pluses can't exist. So I'm adding 8 OH minuses to this side as well as this side. Now, I've selected my H pluses specifically. They're going to get knocked out because these will come together to form what? How many? 8 waters, right? So I'm just going to put a scratch through this like this to kind of show that I've done that part. This now exists as 8 waters. And then my 8 OHs still exist over here because there was nothing for them to combine with, right? This looks like it was balanced in base because there's an excess of OHs, there's no excess of H pluses. One more simplification step though. The waters need to be taken care of, right? So I've got 8 waters on the reactant side, 4 waters on the product side. What do? Cancel out all 4 of these, right? Because these 4, it's redundant to write it twice, right? So these 4 are totally knocked out. And this leaves me with how many on the side? 4. And I like for you to walk yourself through it like that because then you're not trying to do about 5 steps in your head. You could, like you are totally capable, but it just helps you not get confused. So my final reaction should be 4 waters, 2 chromates, plus 3 sulfides yield 2 CRO, 2 1 minus 3 S's, and 8 OHs. So when I say balance in acid, you do the first blah, blah, blah steps. If I say balance in base, do blah, blah, blah steps, and then reflect to the bottom. Do I have H pluses? Yes. Get rid of them by putting OHs on both sides, and then simplifying waters. Okay? So let's go ahead and do, we got 10 minutes left. Let's do, we just did 1 together on the balancing bases. Let's do 2. I'm going to assign minimal here because it is redundant, I know. Let's do 1, 2. Four. 8 and 10. What do you say? 2, 4, 8, 10. Is that what I said? Okay. So on the bases, you're doing 2, 4, 8, and 10. So finish your ones from acids, complete your ones from bases, and that's it. Take your test tomorrow. You still have 10 minutes, don't waste your time. I think you skipped like probably 10 minutes. You'll learn when you do something live.
Yeah.
Multiple choice or yours? No, don't take a picture. I'd rather you just take it. Who still is not certain their test directions? Don't raise your hand. Just bring it to me tomorrow. And if anybody wants their you review stuff from you turned it on Tuesday to study with, come and get it because I'll give it back to you. I know that I want it back tomorrow, but I want you to have someone say how you need it. Oh, okay. Because it's even the hospital stuff. Like, I'll give you around the stuff. So everything you turned in on Tuesday. This
with this. It doesn't have to be just one. It can be done here.
You know what, kids start looking at this, I'm in the mandatory topics.
Yeah.
You'll probably really
Do that for me and
I was
commit to
thinking
it.
more of like what humans can do to change it.
So, like what? But you know what? Put that on your research, yeah.
Yeah, like that's what I